Hello, welcome back. This is Jonathan Gardner. We're covering Sergey Lang's Basic Mathematics, section 17.5. One more section to go after this one. Oh boy, we're just like so close to the finish line. I'm going to share a quick story. I know that you didn't come here to listen to my stories, but I ran cross country in high school. And for the state, what was it, like the something or other, like it's like the last race of the year. Okay, so the coach on the bus ride up to there, he's like, okay, everybody, I want you to know that this course, there's a small stream like 100 yards from the finish line, okay? He says, it's a small stream. All you have to do is just jump over it, okay? Don't get your foot wet, because if you get your foot wet after running for, the 5 kilometers or whatever it is, you're going to be super tired and it's going to be the worst moments of your life, right? So if you do get one of your feet wet, don't get both feet wet, right? Anyway, as you can imagine, as I'm coming through to the end, I'm feeling great. I'm getting a good time. And then I go to jump over the stream, but in my lack of strength, one of my feet lands in the stream. And so I take my other foot to pull the foot out, and it slips and lands in the stream as well. So the last 100 yards of that race, I had both shoes loaded with water. I was feeling sick to my stomach. Oh, it was the worst. It was the worst. But anyway, it was a great feeling after finishing the race. Anyway, so we're so close, okay? So properties of 3x3 determinants. Again, mathematics is about not doing math. It's about finding shortcuts and tricks and little things so that we can do more math by doing less. And so we are going to do the same thing that we did with 2x2 matrices and determinants, and we're going to do this with 3x3 matrices, right? And we're going to prove D1 through D6, and it works for 3 matrices as well. However, note that when you have a 3x3 matrix, this is the same as basically taking 3 columns and multiplying them together, So we are going to assume that everything has a dimension of 3. Okay, 3x3 matrices, and these row vectors and column vectors have a dimension of 3. Okay, so anytime we have a capital letter, that's not D obviously, we're talking about a 3x3 something, okay? D1, so D1 says that if we have, let's say one of these columns can be written as the sum of 2 other columns, then we are going to have the determinant of A prime, A1, A2, A3 is the same as the determinant of B plus C, A2, A3, which is equal to the determinant of B and A2 and A3, plus the determinant of C and A2 and A3. This is the distributive property all over again, okay? For the proof, we are going to use the definition of the determinant, namely expansion according to the first row, okay? So if we take, why is he doing the first row? I would rather do the first column, but he's doing the first row. So he wants to do a little extra work. I don't know, maybe he's flexing his math skills in front of you. I'm going to do the first column. So for the proof, we're going to take the determinant of lowercase b1 plus c1, b2 plus c2, b3 plus c3, and then we have A1, 2, A2, 2, and then A3, 2, and then we have A1, 3, A3, 2, 3, and then A3, 3. Okay, my handwriting is terrible, but I know where everything belongs. Okay, so this first column is the sum of those 2 column vectors, right? So we are going to get B1 plus C1, because this is the plus. Remember, plus, 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 and minus, 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 minus. Okay, this is plus times the determinant of A2, 2, A2, 3, A3, 2, and then A3, 3. And my handwriting is terrible. Again, I apologize. Minus B2 plus C2 times the determinant of A1, 2, A1, 3, A3, 2, and then A3, 3. All right? And then plus B3 plus C3 times the determinant of A1, 2, A1, 3, A2, 2, and then A2, 3. Okay? I don't want to go any further. Okay? But notice that this is the same, right? This determinant is just a number. I'm not using a black pen. I don't want to use a black pen. So this term becomes B1 times that plus C1 times that. This becomes minus B2 times that and minus C2 times that. And this becomes plus B3 times that plus C3 times that, right? And so this is the determinant of B, A2, A3, and this is determinant of C, then the same. Okay, so that's how we're going to solve that. We're just going to satisfy ourselves there and then move on to D2. If you want to spend more time, if you want to go deeper and study that more, you're more than happy to. Okay, I'm trying to save some trees here. D2. Okay, so D2 says that if X is a number, not a matrix, then the determinant of X times A1, A2, A3 is the same as X times the determinant of A1, A2, A3. Okay? And similarly for the other terms. So it's also the same as A1, X times A2, and A3. And it's the same as the determinant of A1, A2, and X times A3. Very straightforward. Okay? For the proof, okay? So we note that when we take the determinant of X, A1, A2, and A3, we are going to get, I'm going to do the column again. So we get X times A11 times the determinant of A22, A23, A32, and then A33, minus X times A12 times the determinant of A12, A13. This is not right, is it? This is A21, okay? And then A32, A33. And then plus X of X times A3, A11, 21, and 31. Okay, there we go. This is going to be A12, A22, A22, no, A12, A13, A23, and then A23, A22, and 23. Oh boy, okay. Did I make a mistake? Probably. Okay, you get the idea, right? And so we can just factor out that this is X times A11 minus A21 minus plus A31 times these determinants that we just did. And that is just X times the determinant of A. Okay, pretty simple solution there. We also have unit vectors for the three matrices. So we have E1 is equal to 1, 0, 0. E2 is equal to 0, 1, 0. And E3 is equal to 0, 0, 1. Again, these are called unit vectors. And the unit matrix E is equal to 1, 1, 1 down the center with zeros everywhere else. I'm sorry, that's a parenthesis. This is called the unit matrix. Hopefully this is not surprising in the least. You saw this coming from a mile away, okay? And so D3 says that D of E is equal to 1, okay? This should be pretty obvious, especially if you did the last homework problems. I think it was number 4, right? So if you did the last problem, number 4, you're like, oh, I know what this answer is. I've done this before. Okay, D4 says if two columns of the matrix are equal, then the determinant is equal to 0. Okay, so if we have D of A, and B, or D of A, B, and A, or D of B, A. Okay, so any one of those two columns are the same, then the determinant of this is 0. So his proof uses a lot of words, not a lot of math. What he shows is that, let's say we're going to take this determinant. So we're going to take the determinant of A, and B. Okay, so if we expand by the B column, we are going to get B1 times the determinant of A1, A2, A2, minus B2 times the determinant of A1, A3, and A3, and then plus B3 times the determinant of A1, A2, A2, right? So this determinant is 0, that determinant is 0, that determinant is 0, and so the entire determinant is 0. Okay, so we just expanded by the B column here. Pretty simple stuff, not terribly complicated. D5. So D5 states if we add a multiple of one column to another, then the value of the determinants does not change. So if we have the determinant A1, A2 plus X times A1, and then A3, right? then this is the same as the determinant of A1, A2, and A3. Okay? So if we want to prove this, we'll just use the other properties that we've already determined. So we have the determinant of A1, A2 plus X, A1, and A3 is equal to the determinant of A1, A2, A3 plus the determinant of A1, X times A1 and A3, right? And this is going to be that plus X times the determinant, I'm not going to write it that way, A1, A1, and then A3. Okay, and so this is going to be equal to X times 0 because a determinant with the same columns is 0. Okay, and so we're just left over with the determinant of A1, A2, and A3. Okay, very straightforward proof there. Again, if you wanted to prove this by actually taking the determinant, you're free to do that. I have better things to do with my time, but you might want to practice determinants. D6. If two adjacent columns are interchanged, the determinant changes by a sign. So if we have D of A1, A2, and A3, and we switch that, okay? So we say D of, let's say, A1, and we're going to switch 2 and 3, A3, A2, then that's going to be minus, okay? It's also equal to minus the determinant of switching the first two, A2, A1, and A3. It's also equal to minus if we switch, well, that's all we can do, can't we? Right? That's all we can do. Okay? So the proof of this is a little bit involved, but it's not very difficult. We use the same kind of trick we used for the two matrices. So we say 0 is equal to D of A1, A2 plus A3, and A2 plus A3. Right, it's 0 because these two column matrices are the same. And so we expand this out. We're going to get dA1, A2, and A3 plus D of A1, A3, and A2. So we have A2, A2, A2. We also have A2, A2. A2, 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 A3, and then A3, A3. A2, A3, and then A3, A2. Okay, so if we expand this term first, we're going to determine of A1, A2, A2 plus A3, and then determinant of A3, A2 plus A3, and then we expand out those two and we get these four terms, right? So we get determinant of A2, A3, determinant of A3, A2, determinant of A2, A2, and determinant of A3, A3. These two are 0 because they have the same columns. And so we see that these two must be opposite of each other. So we determined that the determinant of A1, A2, A3 is equal to minus the determinant of A1, A3, A2. Anyway, that is a fun one to play with. So I encourage you to try what would happen if you tried to switch A3 and A1. What do you get there? That would be something interesting to try. That might even be a homework problem. I don't know. Okay. All right, so we are going to do an example here using these new rules, right? Because we have determined that we are sick of doing determinants, so we just want to calculate determinants using the rules. So we are going to try to save ourselves as much time as possible so we can get to whatever video game it is that we wanted to play. Hopefully it's not Minecraft or Fortnite, but if it is, that's okay. So we already have a 0 in the first row, so we can subtract 2 times the second row from the third row. Okay, so 2 times the second row from the third row. So this is going to be the same as the matrix of 3, 0, 1, 1, 2, 5. And then so we're going to take minus 1, minus 2, so that's minus 3, 4 minus 2, that's 0, and 2 minus 10, that's minus 8. Okay, so what I'm doing here is I took the logic for columns, but I applied it to rows. Okay, because the transpose is the same. So if I were to take this matrix and flip it, then it would be, so if I were to rewrite this matrix this way, so 3, 2, 2, 1, minus 1 and 4, 0, 1 and 5. Okay, these two determinants are equal. Okay, and so what I did is I took second 2 times that guy and subtracted it from this guy. Okay, and I can do that because when you subtract a multiple of one of the other rows, the determinant doesn't change, right? And then I took the transpose back, okay, and I got this matrix here. Okay, so already we're almost there. So we take 2, because we know that's going to be positive. We're going to take the determinant of this column, okay, and times the remainder of this. So we have 3, minus 8, 1, and minus 3. Okay, so we could at this point solve it if we really wanted to. We could do some more shenanigans, and we can take the determinant of this and add it to that, right? So this row plus that row. So we get 2 times 3, 1, and 0 minus 7. Okay, and we can see that this is just going to be 2 times minus 21. So we're going to get minus 42 as the answer. Okay, see how easy that was? Okay, well, let's do another example. So this is 4, 7, 10, 3, 7, 5, and then 5, minus 1, and 10. Okay, so subtracting 2 times the second row from the first row. So we're going to take twice this and subtract it from the first row. So we get 4 minus 6 is minus 2, 7 minus 14 is minus 7, and then 10 minus 10 is 0. And 5 minus 1 and 10. And then we do 2 times this row from the third row. So we get minus 2 minus 7, 0. And then we take twice this, so 5 minus 6 is minus 1. Minus 1 minus 14 is minus 15. And then 10 minus 10 is 0. Ah, there we go. Okay, so this is plus minus plus, minus plus minus. So this is going to be minus 5 times the determinant of minus 2 and minus 7, then minus 1 and minus 15. Okay, so there was a homework problem for the 2 by 2 matrix. This is what happens if you multiply both columns by the same number, right? Well, in this case, we're multiplying both columns by -1, so I'm just going to change this to this. Okay, because this is the same determinant as this, except multiplied by -1 twice, so it's the same. And I could, again, do some tricks here. So subtract twice the second row from the first row. So we get 0. And then 7 minus 30 is minus 23 or whatever. And then we get 1 and 15. And so we are going to get minus 5 times minus 23 times 1. So we get 3 minus signs means there's a minus sign at the end. And it's going to be 115. So minus 115 is the answer. Okay, that is how you solve determinants. You don't actually sit down and write out and multiply all those things. You can if you want to, but you play these mental video games with yourself and you figure out how you can use the properties to try to solve these things as quickly as possible. Let's go over the exercises really quick. Okay, number 1 is write out in full and prove property D1. That's pretty easy to do. Same thing for D2 is number 2. Number 3, prove the 2 cases not treated in the text for property D4. So property D4 had to do with if 2 columns of the matrix equal, the determinant is equal to 0, right? So just basically if the first and second columns, the first and third columns, and the second and third columns are equal, okay? 4 is prove D5 in the case that you add a multiple of the third column to the first, second column to the first, and third column to the second. Yeah, this is just basically seeing if you understand the proofs. And number 5 is prove D6 in the second case. Number 6, if you interchange the first and third columns of a given matrix, how does its determinant change? I asked that question. So yes, that is number 6. What about interchanging the first and third row? Number 7, state D5 and D6 for rows. So basically take the transpose. Determinant of a transpose is the same. Number 8, compute the following determinants, making the computation as easy as you can. So many of these, I'm looking at number A in particular. I know what the determinant is, and I don't even have to do any calculations. I just saw that something is the same as something else. Okay, so look for patterns like that. Then I'm going to add one row to the other. Number J as well. Also, I know what the determinant is. So number 8J and number 8A, I can tell you the determinant without even doing any calculations at all. That's how fantastic I am. No, I know the tricks, right? I learned the tricks. Number 9, let C be a number, multiply each component Aij, 3 by 3 matrix by C. So we have number 9. We have C times the matrix A is the same as CA1, CA2, and CA3. How does the determinant change when you multiply the entire matrix by C? There's a problem like that back previous sections. Number 10, let x1, x2, x3 be numbers. Show that the determinant of this. So we're going to take number 10, the determinant of 1, 1, 1, x1, x2, x3, and then x1 squared, x2 squared, and x3 squared. and then you're going to get something, and then you're going to factorize it. Okay, so he already shows you what factors you can use. Okay, pretty interesting result there. Number 11, suppose that A1 is the sum of 3 columns. Using D1 twice, prove that you can distribute with 3 terms. Okay, and then he uses this notation. So 11 is kind of interesting. Okay, so he starts. So 11, number 11. So he says you can rewrite this as the sum from j equals 1 to 3 of the determinant of b of j, a2, a3. Okay. In general, suppose that you can write a1 as the sum from j equals 1 to n of b j, right? How would you rewrite the determinant? Okay. How would you do this? This is not that difficult. If you're spending a lot of time on number 11, you kind of miss the point. Number 12, let x, j be numbers. Let a1 equals x1, c1, x2, c2, x3. Prove that determinant is the sum of that. 12 is interesting. Not very difficult. Number 13, state the analogous property that of exercise 12 with respect to the second column, in respect to the third column. So number 13 is just, 12 again. All right, those are the exercises. They're pretty interesting. They're kind of fun. They shouldn't take you too long. If you need help, obviously you can reach out for help on Discord channel. You can put a comment in the YouTube channel here. If you guys have any questions about anything, please ask. The next section is the final section. Take care and bye-bye. This video was part of my series on Basic Mathematics by Sergey Lang. Be sure to subscribe and ring the bell, like and share this video. You can find me on Discord and support me on Patreon. Thanks a million.